Right now, you're looking at a sheet of illuminated glass and metal, but underneath that surface, the images and text you see are being rendered by billions of microscopic switches, flipping on and off billions of times every second. These switches are transistors. A transistor is a solid-state device used to amplify or switch electrical signals and power, serving as the fundamental building block of all modern electronics. Since its invention, we have manufactured more than 13 sextillion transistors. This makes it the most numerous artificial object in history, outnumbering every other tool or component we have ever built. Without this invisible foundation, the digital tools we use to work, communicate, and navigate our lives would instantly cease to function. Before we could etch billions of switches into silicon, computing relied entirely on vacuum tubes. A vacuum tube is a fragile glass bulb that controls electrical current in a high vacuum. They were essentially modified light bulbs used in early radios and the very first computers to manage the flow of power. But they were physically limited. They were massive, they generated high amounts of heat, and they burned out frequently, meaning early computers required constant maintenance and massive cooling systems just to stay operational. To move forward, engineers had to shift from fragile macroscopic glass to a technology based on atomic precision. This shift removed the physical bottleneck on computing power. It allowed our machines to scale down in size, while their internal capability grew exponentially. The canvas for this technology is silicon, an abundant element that forms a rigid crystalline lattice. Silicon is a semiconductor. This means it usually blocks electricity, like rubber, but it can be forced to conduct it, like copper, under the right conditions. To create those conditions, engineers use doping, the process of injecting specific chemical impurities into the pure silicon lattice to change how it handles electrons. This creates two materials: N-type silicon, which has a surplus of negatively charged electrons, and P-type silicon, which contains empty holes ready to accept them. This process transforms inert silicon into a customizable landscape, ready to manipulate the movement of electricity. We build the switch by arranging these materials into three parts: the source, where electricity enters, the drain, where it exits, and the gate that controls the flow. In its resting state, the switch is off. Electricity pools at the source, but a physical barrier in the silicon prevents it from reaching the drain. To turn it on, a tiny, precise voltage is applied to the gate. This voltage alters the atomic structure of the silicon, instantly dissolving the barrier and allowing the electricity to rush across to the drain. When that voltage is removed, the barrier reforms to slam the gate shut. This entire process happens with zero moving parts. It is a purely atomic reaction. Managing vast flows of energy using only the specific arrangement of atoms is the central achievement of the transistor. Once you have a switch that can open and close billions of times without breaking, you can translate physical reality into mathematics. This is the basis of binary code. When the gate is open, it represents a 1. When it is closed, it represents a 0. By etching billions of these switches onto a single wafer of silicon, we create a microchip. Wiring these binary switches together allows us to perform complex logic, enabling everything from high-speed graphics to the navigation systems of spacecraft. The transistor is the physical bridge that allows us to translate the laws of physics into the world of algorithms. In 1947, the very first working transistor was the size of a paperclip, a crude assembly of plastic and gold contacts. In a single lifetime, we've progressed from that hand-built prototype to packing over 50 billion atomic switches onto a chip the size of a fingernail. We have moved from the scale of the paperclip to the scale of the atom. It is a level of precision that has no parallel in any other industry.